I forgot. Okay, so what we had was a source. Source looks like this. And this would be the positive, and this would be the negative. So whatever the source, now this is really a direct current source. That's cranking a generator, which doesn't give us a direct current. Okay, the generator gives us a current that does this. There's electronics in the current, a rectifier circuit that makes all the downs into ups. Okay, so the current is relatively constant. If you're trying to measure the current using our linear interface, it's going to give you something like this. Okay, the current's going to look like this. Now here's 0. It's not going to do this. It's going to do something like this. Okay, it's going to be somewhat random. If you use a battery, it's nice and smooth. If you use one of our official power sources, and I don't like to use them much because there's more to learn by using a battery. But the power source has the advantage that it maintains a constant voltage or very nearly a constant voltage, no matter what's going on in the circuit. Battery has internal resistance. We'll see what the implications of that are later. So that's just a little bit about sources. Right now, we're going to regard our cranking source as a direct current. We're going to symbolize it by direct current. We had an alternating current. Symbol be like this. Okay, that's a symbol for an alternating source. I'm going to erase that. We're not going to do that at this point because we're nowhere near being prepared to deal with alternating circuits. It's pretty complicated. Okay, so anyhow, here we have a source. Now, in this source, we have wires, and it makes a convention that our lead wires with the clips on them, have no resistance. Now that's ideal. We could calculate the resistance. We know the diameter of the wire and the length. Just look up the resistivity of copper, sometimes you get negative 8 meters. Okay? 3 times you come to the negative 8. I tend to forget that from year to year. I don't use it at all. It's just a constant you can look up, and it's really easy to calculate the resistance if you know the diameter of the length. It's not hard to understand that either. Okay, so anyhow, we got these no resistance leads. Okay, then if we come up here to, I don't have a good way to depict this. Because our standard symbol for resistance looks the same no matter what the resistance. We just label it with the resistance. What we've got is we've got one piece of nichrome wire here, and then another piece of nichrome wire here. So I'm going to, I haven't really thought about how to put this on the diagram. I'm going to do it like this. Normally, your symbol for resistance looks like this. Okay, so this is like a long resistor. And the length has something to do with how much resistance. And we'll see why that is. Then over here, we have another long resistor. And I'm going to, you see that I'm making this a little thicker than the other one. Okay, the amplitude of these things, and this has nothing to do with like an alternating current amplitude. Stuff we measured last lab, Helmholtz coils and the rotating magnet and the stuff we got, the graph kind of looked like that. Okay. Okay, so I'm going to call this thin nichrome. And I'm going to make one change to the thin nichrome. It's shorter than the other one. And the length of this thing is going to have a meaning. So I'm going to say, okay, thin nichrome is only this long. And we're going to attach it here. This is thick nichrome. Now let's just say we've got approximately 1 volt. Yeah. I'm going to tap this thin nichrome. With 2 leads, look at the diameter. See how that corresponds to what we did. Okay. And I'm going to tap this thick nichrome, and we could do this both at once if I had 2 working ammeters that I could lay my hands on. Okay. They should all be working, but the first one I tried was working, and the second was one. But the first one that was working worked fine on the 1 amp scale, but didn't work on the 2.5 amp scale. I don't know what's going on there. Take them apart and see if there's a bad resistance. Okay, so the thin nichrome, the thick nichrome. Okay. Tap the thin nichrome. There's the thick. I'll say that distance was approximately 3 centimeters. That's still there. You can measure it. So how close I am. Probably 3 centimeters. Just round it off. Between 2.5 and 3.5. Maybe as little as 2. Probably not as much as 4. Okay. Doesn't matter. We tap these at approximately equal distances because we just did a quick ballpark. So just to get the concept across. So what we found was okay, for the thin, it was 0.4 amp. On the thick, it was 0.1 amp. It was actually the same ammeter. We hooked it to the one and then the other. But again, we had 2 identical ammeters, 2 accurate ammeters. We could have hooked them both at the same time. It wouldn't have made a significant difference. Again, we'll figure out why later. But the idea is that ammeters have a very low resistance, which is why you can hook them in series in a circuit. They don't have much effect when you hook them in series. If you hook them in parallel, which is what we just did, now by series, I mean, if you interrupt the current here or the circuit, you put an ammeter in, then it's in series. Okay, and we did that. We found that we even tweaked that little generator, we get a lot of current. There's not much resistance, even in the nichrome. There's some. Okay. If we hook an ammeter in parallel, we better darn well be careful. We hooked it at close points and found that Yeah, there was a voltage between here and here. Whatever the resistance of this ammeter is, we could use that voltage to determine from the reading on the ammeter, we could determine the resistance of the ammeter. Now, we haven't even defined resistance, but that's what we know. So there's ballpark thing, and we conclude might be a little hard to read. 4 times the voltage drop on the thin wire over the same distance. Now, the distances weren't totally identical, they're pretty close. So this is only a ballpark, but it was pretty clearly close to 4. Probably wasn't 3, it might have been 5. It had a little less than 4/10 of an amp actually, and a little less than 1/10 of an amp. That's what it looked to me, but I was busy keeping the generator steady. So I only took a quick glance. So we're going to repeat the experiment. You're going to repeat the experiment, but you're going to measure it more accurately. Now, what's going on here is when you do the experiment, it helps to have a picture of what's happening. Okay, so let's just say we've got a length of thick wire and a length of thin wire, and we got some voltage across this. Let's say we got 1 volt. Well, maybe it's 1 volt. We don't know. We haven't measured it. Okay. So there's our circuit, and these are our resistors. Remember what a volt is. It's a voltage. It's potential difference for unit of charge. Okay. Joules for Coulomb. Okay, so now we know that to move a Coulomb current or Coulomb of charge from here to here takes a joule of energy. How does a current move the charge? Or how does a voltage move the charge? Well, electric field. It's force over charge. I shouldn't say N, it should measure N. students' Coulombs. Now, where are the Coulombs? Well, the Coulombs are there in free charges. And we're not going to talk at this point about conduction bands and so forth. Just take my word for it. There are free charges here that get to move through the wire, but there's some resistance to the motion, which is why it takes energy to make them move. Okay. Where do you have more charges available? Assume these are the same material, which I think they are, both nichrome. Okay. So these are the same material. Where do you have more coulombs charge per unit of length? Well, it's going to be here because you got more wire per unit of length. Okay, so okay, so the charge per unit of length is greater in the thicker wire. Okay, now I'll digress for a second. You got copper wire here. You got nichrome wire here. Okay. There are differences in the material. Maybe you have more available charges in the nichrome and in the copper. And maybe there's more available charges in the nichrome. By available, I mean charges that are free to move. They're not totally free to move. Okay. Because I can't talk about the quantum mechanics of it right now. But you can think of it as I don't like to use sticky. It's like the material sticky, so that they got some stickiness to overcome the move. It's actually a quantum mechanical phenomenon. The usual analogy is there are more atoms. The atoms in the crystal structure of the metal interfere with the motion of electrons. Okay. And you can model the electrons as waves. So it's like the waves are interfered with by the atoms. That's way oversimplified. It's probably the best. Okay. So think of the electron as a wave, and it's hard to think of an electron as a wave because it is a particle. It's actually both, depending on how you measure. Not going to talk too much about that now. We'll talk about the role of the collateral. So what happened there? Different materials have different concentrations. The word I should use is density. We only use concentrations. We have a little variety in the vocabulary, but we're talking about the density of free electrons. The number of free electrons per unit of volume. I'll even use term. Different concentrations or densities of available electrons. And interfere differently. through the material. Okay. The other thing you want to understand before we get to rigorous definitions, in that, let's say one of those copper leads, you might have 1,000 coulombs of available electrons. Okay. In a mole of copper, you've got 100,000 coulombs. Okay. So electrons, if you only got 1 electron per atom. Now there are a lot of electrons in copper atom. With the atomic numbers, maybe 50. Okay. But most of them are bound tightly to the nucleus. The electrostatic charge nucleus really attracts those electrons. They don't want to go away. So there's only 1 or 2 electrons. The copper has a valence of 2. The outer electrons, you got 2 outer electrons. You've got chemistry, you know what valence is. Okay. Just the electron shells. You got an outer shell with 2 electrons that aren't all that tightly bound. Well, then it gets a lot more complicated, but essentially those electrons get shared by all the atoms and they're free to move along. Okay. So in this length, you might have 1,000 coulombs of electrons. If you have a 1 amp current, that corresponds to the electrons in 1/1000th of that length actually passing a given point at a time in a second. Okay. Which means if the wire is 50 centimeters long, you get that 1 amp current. And, you know, 1 amp's kind of enough to kill you if it goes through your heart. Actually, 1 amp might freeze you. 1/10 of an amp, I think, will kill you. 1 amp just freezes your heart. 1/10 of an amp just confuses the electrical signals in your heart, and it stops beating right. That kills you. 1 amp through your heart. It's kind of what you do to defibrillate somebody. You freeze the heart, and you release it. Okay. They don't keep it on there too long because it's hard to get an amp through your skin. Skin has very high resistance. I'm digressing, but just to get a little more picture of what an amp is like. Get an amp through your body, it really, really hurts. That's an amp really hurts. Okay, an amp through this wire means the electrons are drifting along here at half a millimeter per second. Barely perceptible motion. Although if you pick out your favorite electron and watch it for a minute, which you can't do, but you can't watch it. But it would, in a minute, it would move maybe 15 millimeters. Okay. So if you look at it, you don't really see it moving. But in a minute, you see that it's a change of position and you can tell that it's moving. Now that's a kind of a bad analogy because the electrons are actually bouncing around in there at over 1,000 meters per second, randomly bouncing around. Okay. The drift, okay, it's like the electrons form a cloud, and there's all kinds of motion within the cloud that's not directed at it. It's likely to be going this way, is that way, or that way, or that way. You impose a voltage on here. You impose a certain number of joules per coulomb as a result of your electric field, which imposes a certain number of newtons per coulomb, which could be converted to newtons per electron. Okay. You know, 1 newton per coulomb would be like 1.6 times 10 to the negative 19th coulombs per electron. And that's enough to cause the electrons to really accelerate. And pretty soon they bump into another electrons bouncing around, they get knocked back. So they just kind of have this random motion that gradually moves along the wire. And the whole cloud then drifts along the wire very slowly, in this case, 0.5 millimeter per second. Does that make sense? Picture makes sense. You're going to read about it. Okay. Okay, so back to what's going on here. In this wire, you've got more available electrons per unit of length than you have in this wire. So if you tap off equal lengths here and here, in which one are going to have the greater drift velocity? Going to have a greater drift velocity here because the same number have to get by every point here in any given unit of time as here. So if you look how many drift by here in a minute, it's got to be the same as how many drift by here. Why is that? Because if the electrons bunch up anywhere in here, well, it's a conductor. What happens in a conductor? If things bunch up, they repel each other. And they can't bunch up. Okay. So the electric field in an isolated conductor has to be zero. Now, in a conductor where you're opposing a voltage, that's not necessarily the case. Okay. So we'll worry about that later. Okay, so the drift velocity is less here than here. So use the word drift. I'll say we have equal charge drift per unit of time here and here. Okay. More charge is available per unit length. Here. Okay. Not the greatest diagram I've ever done. That was bunched up, but okay. I'm going to get to live with this. You have equal lengths of these two wires made out of the same substance. Then slower drift. Actually, I don't even have to say that. You got a slower drift. And this is a consequence of this, which is a consequence of this. Same current, slower drift. What we just measured indicates that it takes more joules per unit of length here than here. Okay? Because in order to make the electrons drift faster, you need more newtons per coulomb. Same number of coulombs per second, so you need more joules. Let them move. Okay. So it comes down to that. I'll work out the total model. Second concept here about it. Yeah, let me take the thought I have there. You get fewer electrons. Okay, they got to be moving faster. Okay, it takes more energy to move. So, as a result, more volts, which leads to more amps through that end. That's what it really comes down to. Now, there's this idea of current density. I've been talking around it. The current density not joules, got an arrow over it. Okay, it's a vector.
Okay, we get it. All right. Everybody else knows.
Current per cross-sectional area times vector in the direction of the current. Now, current is usually denoted by I. If I want to put an arrow on this, a vector on this, because this is a vector, this is just a scalar quantity. There's a vector here that indicates the direction, right? I don't want to use I, although I is associated with current. And I don't remember letter textbook uses. So I'm just going to use V. And I'll do a V hat, indicate it's a unit vector. Okay. Where is the current density greater? In the big wire or the little wire? The fat wire or the thin wire? Pause this for a second. Discuss it. Okay, well, got a real good explanation. Basically said, got the same current running, you got less cross-sectional area, so you're going to have more current density. Okay, that should be intuitive as well as just looking at the equation. So, it's complete. Okay. V is the unit vector in the direction of the current. Just got a notification that the college is going to close in 20 minutes because it's getting breezy outside. I'm not really happy about the necessity of calling off school because of a breeze. Actually, it's going to get pretty windy. And I don't know that the people here that made that decision had any real choice in the decision. There's a liability. Don't want anybody getting their hair on themselves. Now, I don't know how windy it's going to get, but you know, somebody in frail health. But if you look at your health good, I don't think it's a danger to any of us, but don't take it lightly. I mean, seriously, stuff can blow around and hit people if it gets that windy, and then debris gets to be an issue. It's the way to find out. And we're on top of it. So maybe it wasn't a terrible decision, but still, I think bothering people too much. Okay. Not sure what to do. Well, okay, your current density. What do you think drives the current density? Yeah, well, here you are. You're an electron surrounded by a bunch of other electrons. What does it make you move? It's an electric field. Okay. And the electric field then accelerates us all. And you know, it accelerates us really quickly. I mean, it just a very tiny fraction of a microsecond, we'd be up near light speed. Except there are other things around, other electrons coming at us because they're moving around randomly, so we don't get very far. Okay, a few nanoseconds, we're going to run into something. So we all start drifting. Okay, well, that's what drives the current density. If I just consider the electrons in a small section of the wire around me, I know I know how many electrons there are, then I know how much current is going to be. It's not quite exactly accurate to get the idea. And what it comes down to then is that is proportional to E. Current density is proportional to your electric field. Okay. It's a little more complicated than what I said, but not much. The proportionality constant depends on your material. Okay. Okay. Now we've still got 16 minutes. And we're going to actually do some measurements to see if we really do get a 4-to-1 ratio. Or is it 5-to-1? Or 3-to-1? We're going to do some accurate measuring. I think I might have defined your voltage due to a charge Q is the integral of the force per unit charge. Okay. And of course, let's say the charge is little q, big Q was your test charge. Put a T on that. Well, be the word the test charge. Of course, that's the integral. Okay, little q over r squared dr. Well, this is the work done by the field. This is a work by conservative field, and this is a work by conservative field. Okay. What's the definition of potential energy? It's equal and opposite to the work done by conservative forces, which is the way I've consistently defined it throughout the course script, both semesters. Okay. I didn't use that definition because I was busy, trying to get you to do the integral and stuff like that. Again, no excuse. So this will be the negative change in potential because delta V is change in potential energy. Okay. Yeah, okay. And I'm still writing stupid stuff down. Quickly. This is changing potential energy per unit charge. Okay. This is work per unit charge. Okay. This is a work conservative field. This is a work per unit of charge. And the main thing is that minus sign. So I'm going to write this as delta V as the negative conservative work divided by test charge, which is then going to be the negative for this interval, which of course is going to be KQ over R from R1 to R2. That's negative. And there's your definition of electric potential. So we're out of time. We need to go with freedom a minute late. So we need to close. So there we go. Okay, I was in a hurry again to get to something else. That was early closure today. And again, no excuse. I should have written down and thought about what I was writing down. Wrote down this interval, which we did the other day. And the whole point is that the voltage is not based on this interval, but the negative interval. So, quick explanation. And I wrote this as change in voltage. This is a change in potential energy. Okay. This is the work done on the test charge by the field created by the charge small q at distance r. Okay. This is the force. We integrate the force with respect to position, and we get the change in potential energy. Then I put a QT down here, which is totally appropriate here. That off to the moment. Okay, again, this is then the work per unit of. It's all messed up. I'm gonna close this down and rewrite it. And well, I'm not going to close it. Zoom down, but we're going to pause here. Okay, so just slightly labeling. What we have here is the work done by the conservative field in moving the test charge from R1 to R2. Okay, that's the work done by the conservative field. Change in potential energy is equal and opposite to the work done by the conservative field. So this is equal and opposite to the change in kinetic energy. The work by the conservative field is equal to the negative of the change in potential energy. Now, voltage, I'll put a 1, 2 there. I was attempting to, but I was in a hurry to get this in before we were obligated to break out the premises. And that's no fine to me. That's my own risks. Okay. Well, the change of potential energy between point 1, 2, 1 and 2, which is are implicitly at distance R1 and R2 from the charged small q, is defined to be the change of potential energy per unit of test charge. It's your definition of potential difference. And that's then going to be equal to negative AQ over R squared, because when we divide by QT, we divide this QT, which of course is constant. So outside the interval, all that stuff. Okay, so we get this. There's our change in potential. This is called the change in the potential, the electric potential. Change the potential difference over per unit of test charge. 22 points. Okay, so there we have it. Now, I have something about here about what potential energy change is. Again, I think there's more attention to what I was doing, but I think done fairly a whole lot. Okay, so right there it is. And another way of saying that is this is equal to the negative of the work done by the conservative force per unit of test charge, which is change in potential energy per unit of test charge, and so forth. And then this comes out integral sign here. Well, you know, the antiderivative 1 over R squared is negative 1 over R, so the negative sign goes away. We get this, and we conclude the delta V 1, 2 equals KQ over R2 minus KQ over R1. And relative to infinity, this is going to be V2 minus V1. There's your PE at 0.2 relative to infinity. There's your PE at distance R1. PE. I think I might have said Q when I should have said R. This is your potential energy of due to the point charge Q at distance R2 minus the potential energy of the charge Q at distance R1. Potential energy relative to infinity. And again, yes. Right, that PE for QT. Delta PE in this situation would be potential energy change from infinity to R. And of course, you have a negative here. You have your instead of potential energy relative to infinity, I want to say potential relative to infinity. This integral, and you can do that integral easily, and you get KQ over R. So, you know, this is KQ over R. Evaluated at distance R2, KQ over R, evaluated at distance R1. There's definitely. Believe the signs are consistent. If not, maybe do a separate video and cut this one out. Okay. Very seldom do that. I usually just show you my mistakes. Okay, just to double check if the signs make sense, let's take the simplest possible case. We have a positive charge here. Here we have a positive test charge here that's going to be moved to here. So we start here, we go here. This distance is R1, this distance is R2. Now what's going to happen if we just release this thing and there are no other forces? It's going to be repelled, it's going to be end up here, and it's going to be moving. Okay, so it's going to gain kinetic energy. If we have intuition about potential and kinetic energy changes, we realize then an increase in kinetic energy in a situation where all the forces are conservative goes along with a decrease in potential energy. We've got potential energy here due to its position. We release it, it gains kinetic energy by losing potential energy. Let's see if these expressions make sense in this case. Potential energy here is going to be higher than the potential energy. Okay. So potential energy here is going to be, that's, yeah, I'm talking about potential energy. Potential energy per unit of charge. KQ over R1. Here, your potential energy per unit of test charge is KQ over R2. Which potential energy is greater? Well, R1 is less than R2. If you divide by R1, then you're going to get a bigger result than if you divide by R2. So this will be your V1. This will be your V2. Or your change in potential from position 1 to position 2 is, well, it's potential you have when you end minus potential you have when you begin. And negative. Okay, because V1 is bigger than V2. V1 and V2 is bigger. Now, you can do all kinds of things with symbols, and then the intuition is, okay, we're closer. Here. It took more energy to move from a great distance to this point than it would take to move from a great distance to this point. So when we move from this point to this point, whatever excess work we did moving from here to here, we get back in the form of kinetic energy if we release this stuff. You want to work that out with the whole idea of energy conservation. If all the forces are conservative, then the change in kinetic energy and the change in potential energy are equal and opposite. If they're non-conservative forces present, then that's not necessarily, that is going to be the case. And you have to take that into consideration. And I believe we've done a lot of that in previous semesters. This is very important. It's very important for what we need to understand about electrostatics and electromagnetism. I just noticed one more bonehead error. But in this integral, ordered this, it's KQ over R squared. Obviously, when you do the integral, that's why the negative sign is important. Okay. I'm probably going to trash this whole explanation and do it in a separate video.